actually go and get to the material that you're quote unquote going to be tested on. All right, and this is what people call the ratio test and the root test. And so these are two really these are two of the major workhorses that people typically use when you're trying to test for convergence. So again, think about the strategy. You look at an infinite series. First, you do the test for non-convergence, okay? So let me just reiterate this really quick. First, we try the test for non-convergence, okay? We test to see if the limit of the sequence terms we're summing up don't go to 0. Okay, chances are on an exam problem, they are going to go to 0, okay? So we can't use this test. Then you look at series that you know how they converge. So we have telescoping, we have geometric, and after the integral test, we have the P-series. And most likely what you're going to find is that it is none of those. Okay, so now we're going to have to use an actual test for convergence. So we looked at the integral test. Okay, we know if we have a positive series we're adding up, and when we replace n, we have an integrable function. We can use that test. We just talked about the comparison test, and I'm only going to talk about one version. There's actually another version. And we may find that neither of those work, or it's kind of a gamish. That is a mixture. So notice the last problem I claimed is kind of a mixture. I started off using the comparison test, and I claimed that I can then use the root and the ratio test to finish it off. And this is very common. This is very similar to when you guys were looking at methods for integration. You started off with one method of integration, and what would happen? Well, a lot of times you had to go ahead and use a second method, right? Same sort of thing here. So now we're going to introduce this other way of testing for convergence. So here's the overview of the root and ratio test. First of all, are there any restrictions on the terms in the series we're adding up? No. So that's very good. That means if we have negative terms, notice if we have negative terms, we cannot use the comparison test directly. Neither can we use the integral test, right? So that's a really nice fact. This has no restrictions. The hardest thing to learn is when to use these two tests. And there is no rule written in stone, but in general, when we have factorials, we use the ratio test. And you'll see why. Right now, that statement won't make any sense at all, okay? But we're going to see why the ratio test comes in handy. When we tend to have ratios of really complicated functions, we tend to use the ratio test. And very often, we do kind of what we did in that last problem that I cut short, and I said we were going to come back to. We end up using a gamish of the comparison test and the ratio test, okay? So that's another reason why it's called ratio of complicated functions. And what is a complicated function? Complicated function is one you look at and you go, holy crap, I have no idea how to do this at all. That's a complicated function, okay? When do we use a root test? We generally use it when we have a geometric-like series. In other words, we have an exponential series. We have a series where we're adding up a sequence, and the terms in the sequence are an exponential function. And one of the things I want to really kind of emphasize to you is that you have to liberate your mind. Okay, you're used to e to the n being exponential. It is. But exponentials are very general, right? In fact, if you remember, we actually made the distinction between the exponential function, right, versus the general exponential function. So this is a to the n, where a is greater than 0. So this is called the general exponential function. Okay, but this is called the. So you kind of want to liberate your mind. Get away from just thinking that e isn't the only exponential function. Far from it. Okay, right now with the coronavirus, the really important thing is 2 to the nth, right? Where n is the number of people that are being infected. This is how the virus is actually spreading. It's exponential. To be more accurate, it's 2 to the n divided by 3. Every 3 days, the infected population doubles if we don't take measures. So this is a very important exponential function, okay? All right. So what do these two things tell us? In the ratio test, the reason why it's called ratio is we're taking the ratio of sequential terms in the series. So notice that this is a general expression for the nth plus 1 term in the series divided by the nth term, right? And I'm looking at the absolute value. And I want to take the limit of this ratio of successive terms in the series. And it's going to be rho. It's going to be some value rho, okay? The root test, on the other hand, living up to its name, I take the absolute value of any general term in the series, and I take its nth root, not the square root, the nth root, okay? And I take the limit as n goes to infinity. And again, it's equal to some number rho. And then both of these tests actually work the same way. Both of these converge if rho is less than 1. If this limit is greater than 1, rho is greater than 1, it diverges. If it's equal to 1, the test is indeterminate, meaning that we can't tell using these tests, okay? So the way that we make this decision for both tests is identical. They're computed different ways, but when we're making our decision about convergence on whatever that limit is, we use the same sort of decision rule here, okay? Unlike the other tests, I'm not going to go into why this works, except just to make the observation. I'll state why it works, but I won't prove it. This is based on the geometric series. Okay. So both of these statements are based on using some results about geometric series. And the proofs aren't hard, but we're really not interested so much in the proofs. We're more interested in see how to apply them. So the proof, if you're really interested, it's kind of cool. It's based on the geometric series. And I won't bother to go through that, but that's where the mathematical basis is, okay? We can prove that rigorously. Okay, so any questions before we go on about what these tests are actually saying?
Oh, what do restrictions mean in this context?
Oh, so remember when we did the integral test, we had a restriction, right? The restriction was that the terms in the sequence we're adding up had to be positive, right?
Mm-hmm.
And when we did the comparison test, we just saw the same thing. We had these two infinite series, right? And not only did they both have to be positive, but one sequence that we're adding up always had to be less than or equal to the terms in the sequence for the other infinite series, okay? So that's what we're referring to when we're talking about restrictions. Does that make sense?
Yeah.
Okay, so this is a very general, this is kind of like an omnibus sort of test, okay? Now, one thing I want to bring up, and this is really useful, okay? When you have infinite series and you have negative terms, the way that they usually come up is they usually come up something like this. You have basically a -1 to the nth power being introduced somehow, okay? This is actually called an alternating series, all right? In other words, where the sign of the terms alternate, you can see that as n is increasing and going from even to odd, these terms go from positive to negative, right? When you have a series like this, it's a good thing to try the convergence of just the absolute value of the infinite series. And the reason why is, first of all, you get rid of that annoying negative sign, okay? But the other reason why is a mathematical fact that says, if this converges, so does this, okay? So if I can show that the infinite series of the positive terms converges, then I've shown that my actual series converges too. All right? It's a very useful fact. So a good thing to do when you have a series involving terms where the sign alternates is just to ignore the alternating sign, work with the absolute value, work with just the positive version of those terms, and see if that converges. And if it does, then you're automatically guaranteed that that converges. Okay, that'll make life a lot easier. Another thing to remember is that very often when you're doing these problems, you're going to have an infinite series that can be written as a sum of two terms. And a really good thing to do is to try to split them apart. Okay? And you can show that if when you split them apart, each of the infinite series for the terms that you split apart converges, then your actual infinite series for the sum of those two sequences, terms being added together, also converges. Okay? That's a very useful fact. The last fact is what we just talked about a second ago, is that when you have natural log of n, you can replace it by n, and you're always guaranteed that it's true. And you also know that asymptotically, the natural log of n is asymptotically less than or equal to n to the alpha for any alpha greater than 0. So these are the three little tips that are often going to help you, okay? All right? So let me kind of just illustrate the thinking that's going on here, okay? So notice I have this infinite series right here, okay? And I have a ratio, and I have a bunch of really complicated terms here, okay? One of the things that you can do is you can look at the leading terms, okay? And so, well, I'll tell you what. Let me not use this, okay? Let me skip this. I'm going to leave this. There, let's not use this hint right here. I'm going to skip over this. We actually have enough with these three facts that we can start to do problems, okay? So this is our test. This gives us an idea as to when we want to use it, but we're going to see that it takes some work, okay? This is very much a trial and error sort of process, okay? And these are the three hints we want to use. When we have negative terms in our infinite series, ignore them. Do the convergence on the series with just the positive terms. See if that converges. Then we're guaranteed our problem converges. If we have a series of sums, split them up, okay? And we want to use what we know about the asymptotic growth of functions. These are the three things that are going to come in handy. Okay, so let me do the following. I'm going to go ahead and I'm going to work through a few problems here, and then I'm going to post, I think I have about 14 problems that I want you to work through. And we'll actually get together and we'll discuss these on Wednesday, okay? So these are all of the problems. How many do I have? 1, 2, 3, 4, 5, 6. Yeah, 14. So I'm going to work a few problems here. We'll kind of go through the logic, okay? And I'm going to have you guys work these. On Wednesday, I'm not going to have a formal lecture. I'm going to just kind of work through the solutions. So maybe for Wednesday, a really good goal is to try to get done with the homework from chapter 10, section 2, and maybe try to get up to it at least the first 4 problems here. Okay, that would be a good goal to shoot for. All right, the more you can do, the better. And I will post the answer key, okay, also. I don't have the answer key made right now, but I'll work that out. Okay, so let's go ahead and try a few of these, okay? So, and one of the things I want to emphasize, because I know that this is a problem for a lot of people, is I want to try to emphasize how we want to write out the solution, okay? So, first thing I want to do is I want to think about what these terms are like, right? So I have an is equal to n factorial over 10 to the nth. Now, the first thing I'm going to do is I'm going to try the test for non-convergence. Okay? So what does the test for non-convergence say? I'm going to skip to another page, okay? So first I'm going to use the test for non-convergence. These are the terms of the sequence I'm adding up, right? So the test for non-convergence says that if the limit as n goes to infinity of the a_n's is not equal to 0, this tells me what? Anybody? These guys that I'm adding up are not getting smaller and smaller and going to 0. What happens as I sum them all up?
Does not converge.
It doesn't converge. It most likely is going to diverge, but it might be bouncing around, right? Does everyone understand why this is true? I wanted to stop for a second. Does everyone understand why this statement is true? Is there anyone that doesn't? Seriously, I'm being serious. Everybody understands why?
This is because there's a factorial on the top and an exponential on the bottom.
No. I'm talking about just this statement right here. I just want to think about this statement. Forget about the problem. Does everyone understand why this statement's true?
No.
Okay. Good.
Not really.
I mean, it's not good you don't understand, but it's good that you're saying it's okay. Let's suppose that this converged to some other value. Let's suppose it didn't converge to 0. Okay. Let's say it converged to 1/10. Okay. So what does this mean? Well, this means if we look at the series terms, right? This is n, and this is 1/10. It means that the values are getting closer and closer to 1/10, right? That's what this means. And what it means to say that the limit as n goes to infinity as an goes to 1/10 means that you tell me how close you want to be to 1/10, and I have to find some index capital N such that once I go beyond that, I'm as close as you asked me to be to 1/10. Okay? Does this make sense so far? Seriously. This is what it means for something to approach another number. It means that I can get as close as I want. And what it means is once you go past some point, once you tell me how close you want to be to 1/10, after you get past some index, I have to always be within that little window. Okay? So suppose you tell me, I want you to be within 1/5. I want you to be within 1/20th of 1/10. Okay? In other words, I want you to be from 1/10 to 1/10 plus 1/20 to 1/10 minus 1/20. Okay? If this is true, then there has to be some capital N after which all of the sequence terms are at least this big. This is 1/20, right? So what this means is that for all n past this index, the a_n's are greater than 1/20. Well, if I sum all these terms up, right? Let's just totally forget about the series. Let's just start at capital N and go to infinity, right? This means that this is going to be greater than this infinite series. Okay? In other words, if I summed up 1/20 an infinite number of times, this infinite series is less than this. What is this infinite series right here? If I sum up 1/20 an infinite number of times, what do I get? Well, if you sum it up enough times, it's going to become infinite, right? Notice that a number, no matter how small, if you sum it up an infinite number of times, you're going to get infinity, right? So this is what tells me this infinite series has to become infinite. Okay, if it doesn't converge to 0 and it converges to any other value, basically I can figure out that the a_n's have to be greater than 0. They have to be greater than actually a finite value, some finite value past some point. And that's what causes this guy to diverge. Does that make a little more sense?
Yes.
Okay. All right. So that's what's going on here. This is actually called the Archimedean property of the real numbers. It says that any real number, no matter how small, if you add it up enough times, eventually becomes infinite. Okay. Okay. So let's test for non-convergence. So I think it was Anil that was talking about the factorials, right? Was that right? Or who was it that mentioned the factorials?
Me.
Okay, and me is who?
Nissan.
Nissan. Okay, so now this was all on the side. Okay, let's go back and apply the test for non-convergence. It turns out that this problem is only one line. Okay, so I gave you all this extra information. But when I do the test for non-convergence, what do I find? Well, let's see. So in this problem, when you apply the test for non-convergence, here's what we're testing. We're testing, does the limit as n goes to infinity of n factorial over 10 to the nth, does this equal 0? The answer is no. Why do we know that?
Is it because that like the like factorial is greater than the like exponential?
Right, it's asymptotically greater. Wait, we look at the classes of functions. This is a general exponential function. This is a factorial. What we know is true is the opposite. Okay, so because we know that exponential functions are asymptotically less than factorial functions. What this means is a limit as n goes to infinity of any exponential function. It's true for any exponential function, okay? So it's true for 10 to the nth over n factorial. That goes to 0. But if this goes to 0 and I'm looking at the reciprocal, what does the reciprocal do?
Infinity.
It goes to infinity. So the answer is absolutely not. So notice that you don't have to do any tests at all. You're already done. I want to take you back to this just really quickly. I want to show you this, okay? So when I was doing this MATLAB, this is back in video 3C, okay? And where was it? Didn't I show you guys that MATLAB code? Where was it? Didn't I do that, guys? Didn't I show you the MATLAB code here for the different functions?
Are you saying in one of the videos?
Yeah, didn't I? Well, yeah, here it is.
I think,
Oh,
yeah.
yeah. What the heck? I know that I did it. Maybe I didn't. Oh, I definitely should post it. I thought I posted it. Anyhow, did I post the plot of the MATLAB code for the different types of functions? Yeah, here it is. It's video 3A. Sorry. Okay. So notice this is what's going on in 3A. So here I plotted x squared for my power function, e to the x for my exponential, and n factorial. And what I want to draw your attention to is this is the exponential function, and this is the factorial function. Okay, and you can see after a while that there's no contest. This is only going out to n equal to 7. Okay, you can see that this ratio as n goes to infinity of the exponential over the factorial is going to go to 0. Okay, that's where that's coming from. Okay. All right, good. So notice that there's actually no work at all. You simply do the test for non-convergence. It fails the test for non-convergence, so therefore it does not converge. Okay. So therefore, you guys don't mind if I use these 3 dots? Is everyone familiar with this? If you aren't, just say so.
I'm not familiar with it.
Okay, this is just shorthand for therefore in math. Okay, just 3 little dots. Okay, I told you guys before, us mathematicians are lazy, right? We don't like to write things out. Okay, so this is not equal to 0, which implies by the test for non-convergence that our infinite series does not converge. Okay? This is why it's so important to try test for non-convergence. Now, first of all, so everyone understands what's going on, what happened here. Okay? Now, suppose you didn't see the test for non-convergence. How could I do this? And by the way, this will happen. And I'll also make the comment too. There are some problems where it's actually hard to test to see what that sequence converges to, okay? So sometimes you have to use some facts about asymptotic growth, and sometimes it's a little tricky. So suppose we didn't try to use the test for non-convergence. Well, I go back here and I look and I say, what do I have? I have a factorial, okay? So let's try the ratio test, all right? So here's what the ratio test says. So let's go ahead and try this a second way, all right? So if I were to try the ratio test, my an is equal to n factorial over 10 to the nth. And the ratio test tells me, look at the limit as n goes to infinity. I don't need the absolute value, right? Because they're all positive, right? Of an plus 1 over an. Now, I have to simplify this, okay? So let's just look at the algebra here a little bit, all right? So a sub n plus 1, what is that, by the way? Remember what we said about series being like functions, right? If f of n is equal to n factorial over 10 to the nth, what is f of n plus 1 equal to? Well, what are you doing with a function? You're taking whatever's the argument and you're substituting it in, right? So here's what I claim. I claim that, and I'm going to leave this for you to think about a little bit, is an plus 1 is equal to n plus 1 factorial over 10 to the n plus 1. Okay? Instead of substituting n, I substitute n plus 1, right? Alrighty? So I'm going to go ahead, I'm going to substitute these in, okay? So this is going to be n plus 1 factorial over 10 raised to the n plus 1 power. And it's going to be divided by an, which is n factorial, divided by 10 to the nth. This is my an plus 1, and that's my an, right? And we know never divide by a fraction, multiply by its reciprocal, right? So this is going to be limit as n goes to infinity. And I'm going to bring this guy upstairs, and I'm going to flip him, right? So he becomes 10 to the nth over n factorial over n plus 1 factorial over 10 to the n plus 1. Okay? Now I have to simplify. Okay, before I go any further, any questions about where we're at right now? How we got here? Any steps? Okay? And what I'm going to do is I'm going to kind of group like terms here, okay? So I'm going to write this as the limit of n factorial to the limit as n goes to infinity, of n plus 1 factorial over n factorial times 10 to the nth over 10 to the n plus 1. Okay? And this simplifies. This is just 1 over 10, right? So this is 10 multiplied by itself n times, 10 multiplied by itself n plus 1 times. What does this right here simplify down to? The factorial part. Okay, so let's kind of look at this, okay? What does factorial mean? Well, factorial means this. 1 factorial is 1. 2 factorial is 1 times 2 times, 1 times 2. Sorry. 3 factorial is 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4. So what do you think n factorial is? What am I doing? I'm multiplying all the positive numbers from 1 up to n, right? So n factorial is 1 times 2 times 3 times 4 dot 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 n, right? What is n plus 1 factorial? Well, I'm multiplying all the numbers from 1 up to n plus 1, right? So this is 1 times 2 times 3 times 4 times dot 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 times n plus 1. Well, notice what happens. Everything cancels, right? I have a lot of cancellation here. Everything cancels because they have the same factors, right? Except for the n plus 1. So this is equal to n plus 1. Okay? So again, remember what I want to do in the ratio test. I want to evaluate this limit, right? So what do I know? This is equal to, oops, sorry. This right here is equal to the limit as n goes to infinity of n plus 1 over 10. This is my rho, right? Sorry, for some reason that's not writing clearly. Let me write that again. So this first product reduces down to n plus 1. The second product reduces to 1 over 10, and I get this, and this is my rho. So what is that limit? That limit's infinite, right? So what we showed that the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to infinity. And what does the ratio test tell us? Well, the ratio test tells us that if the limit of that ratio is not less than 1, we know for a fact it doesn't converge, right? Let me go back here for a second. The ratio test tells us that if it's less than 1, it converges. If it's equal to 1, we can't tell. And here it's definitely greater than 1 because it's infinite, right? So we automatically know that it doesn't converge, that it actually diverges. Okay? So I want to go back to this observation that I made that you can use a more complicated test. I can figure out that series does not converge using the ratio test, but using the test for non-convergence is much, much quicker. It will save you a lot of time. So we know that this does not converge. And it's either by the test for non-convergence, that's the easy way, or the ratio test. Either way. Okay? All right. Okay, everyone good so far? Is that looking all right?
Why doesn't n plus 1 factorial start at 2 instead of 1?
It's just a definition. So the definition of n factorial is that it's the product of all the natural numbers from 1 up to n.
if the equation was, well, not equation, but if it was like n plus 2 factorial, would it start at 3?
No.
Would it?
So this is a set of instructions. So n plus 2 factorial says multiply up to. This is telling you what to multiply up to. We always start with
okay. Makes
so
sense.
2, 3, 4, 5. So we go out to n times quantity n plus 1 times quantity n plus 2. And it's interesting that this grows so fast. If you type in your calculator 70 factorial, a lot of the calculators can't even do it. It's that large a number. Okay. Other questions that we have? Okay. So let's look at this problem right here. Okay. We want to look at this and try to figure out if this converges or diverges. Okay. So n equal 1 to infinity, natural log to the nth raised to the nth power divided by n to the nth. This is a hard problem. I mean, to look at this, it's maybe not so obvious what's going on. Okay. Notice that this function here, is this a power function or is this an exponential function, or is it neither? This is tricky. Is this a power? Is it an exponential or is it neither?
Neither.
The answer is neither. That's right. A power function, the base is the variable, and we have a number here, right? An exponential is a positive number raised to a variable exponent. This is neither. Okay. Remember when we dealt with these problems when we were taking we had like derivatives and stuff like that. We had to take the log, okay, and do like logarithmic differentiation, because these don't fall into any nice category. So this is going to be hard to do. So notice that I'm not going to be able to use the test for non-convergence because I don't know what this thing does as n goes to infinity. I expect it's going to be greater than a to the n. I mean, I kind of know that, but still, technically, it may not be obvious. That's true. So what I'm going to do first of all is I'm going to get rid of the negative signs. So instead, I'm going to consider this infinite series right here. And what I'm going to do is I'm going to try to show that this converges. Okay. So I'm going to try to show this converges. And the logic here is that if this converges, then my original infinite series converges. Our original infinite series with the negative signs converge. This isn't particularly hard to prove, but let's just take this as kind of a common sense sort of notion right now, okay? Okay, I look at this, okay, and I have two tests I can use. I can use the root test or I can use the ratio test. So the question is root or ratio? So not ration. Thinking of the coronavirus here, right? Rations. Okay, so this works well when I have a factorial. I don't have a factorial, or I have a ratio of complicated functions. Well, this is kind of complicated in a way, but when is the root test going to work? Well, notice what I'm doing in the root test is I'm taking the nth root of whatever's in here, right? That's going to help a lot. Notice both of these are raised to the nth power, right? So this is going to work well when I have a ratio, and by taking the nth root, I'm going to be able to simplify that expression, right? So let me just kind of illustrate what I'm saying here. This is my an, right? I can rewrite it this way. Everybody agrees? Right? Okay. Notice if I take the nth root, I'm going to get this. And what are we doing in the root test? We're taking the limit as n goes to infinity of the nth root of the sequence terms we're adding up in the series, right? And I know how to evaluate this limit. So now if we actually try the root test, it's going to be the limit as n goes to infinity of the nth root of a to the n is equal to the limit as n goes to infinity of natural log of n over n. Can I evaluate this limit right here? Yes. Right? This is where the asymptotically less than comes in. I know that the natural log of n is asymptotically less than n to the alpha for any alpha greater than 0. Therefore, for alpha equal to 1, natural log of n is asymptotically less than n. And what does that mean? That statement means the limit as n goes to infinity of the natural log of n over n is equal to 0. This is a fact. So this is my rho, and it's equal to 0. So the root test tells me that if that limit exists and it's less than 1, right, my original series converges. Here. The root test says if this limit exists and it's less than 1, my infinite series converges. So now for the coup de grace. Okay. So limit of n goes to infinity of the nth root of n is less than 1. Therefore, by the root test, my original series converges. Well, actually, this series converges. And since this series converges, this implies that my original series converges. Okay. All right. And I'll post this after class, okay? But this is the logic. Does this make sense? Anything that's throwing people off here? Okay. All right. Now, if you tried the ratio test, here's what happens a lot of times, is there are times when you look at this and you try the ratio test and it won't work, and then you have to try the root test. So if you try the ratio test, it's kind of fun to play around and see what you would have got, right? So just for fun, you know, try the ratio test. See what would have happened. And you're going to see that actually you're going to get, what's going to happen when you choose the wrong test is that you're going to get a limit that you can't easily evaluate. This limit here that you have to evaluate to get rho, you're going to find out for the ratio test, you get a limit, and you're not going to be able to easily evaluate it. So the ratio test is not going to be good. Okay? Okay, questions that we have on any of that? It's good. Okay, last practice problem. And then I'm gonna let you guys work on these problems, and we'll come back next couple days and work on them. Okay. So this last problem, the practice problems, is n to the nth divided by 2 to the n squared. Okay. Again, this is initially it's a very hairy looking problem, right? Not at all obvious what to do. All right. Okay. So number 3 is the infinite series from n equal 1 to infinity of n to the nth divided by, and it's 2 to the n squared, right? Now, let me ask you a question. Which do you think is going to work here, the ratio or the root test? What do you kind of suspect and why?
The root test, because you can pull out an n to, I guess, raise the whole thing to.
That's the question. So what you look at this and you see the n to the nth. If I took the nth root, I'd be able to simplify this. Can I write this as something to the nth power? That's the real question, right? So you're absolutely right. Notice in the last problem, so let's just kind of think about number 2. The reason why that test worked so well, the root test that is, worked so well, is I had a ratio that I could raise to the nth power. And the question is, can I do this here? Okay. So this is where we have to use a little bit of algebra. Okay, so here's what I'm going to do. I'm going to look at the denominator, 2 to the n squared. And this is 2 times 2 raised to the n times n power, right? And I know that this can be written as 2nth to the nth power, right? So whenever you have a to the x raised to the y power, what do? You multiply the 2 exponents, right? But I can go backwards also. Okay, that's what I'm doing here. All right? So this does not look like this, but it is. It's the same thing, okay? And the reason why I did that is I want to cold-bloodedly set it up so that this problem looks like that problem, right? Everybody with me here? I'm using the definition of n squared as n times n, and then I'm using this property of exponents kind of in the reverse direction, right? Okay, let's go ahead and do that. So I can write this now as the limit as n goes to 1 to the infinity of n over 2 to the nth raised to the nth power. Now there's no doubt as to what I want to use. I want to use the root test. Whenever I can express the entire summand as something raised to the nth power, in other words, whenever I can write the an's as some sequence raised to the nth power, that's the red light for the root test automatically. Okay, so let's go ahead and apply the root test. Okay, so the root test says the limit as n goes to infinity of the nth root of an, which in our case is a limit as n goes to infinity of the nth root of n to the 2 over n to the nth power. And of course, we cold-bloodedly set this up because the nth power of something, the nth root of something raised to the nth power is just that quantity, right? So this is limit as n goes to infinity of n over 2n. And what is that limit? What sort of function is this right here on top? Power, exponential, log, factorial?
Power.
Power. Okay. What's on the bottom?
Exponential.
Exponential, exactly. So what do we know about their limits? I know that the power is exponentially less than the exponential. So that means that the exponential wins. That's what it means to be greater than. It means that it dominates, right? As n gets really large. So this limit goes to 0. Okay, so rho, which was the value of the limit, is equal to 0, which is less than 1. Therefore, by the root test, we know that our original infinite series converges. Pretty cool. Okay. So this is kind of a foretaste of how these things go. Okay, this is the sort of way that you want to start thinking about these, and it takes a little bit of work. I mean, you know, very often you work these and you end up getting experience, and you know what experience is. Experience is what you get when